Welcome to this lesson on functions. Previously, we used several of Python's built-in functions. Here, we will write functions of our own. Functions are useful chunks of code that allow you to encapsulate a task. Encapsulation is a way to carry out a whole series of steps with one simple command. For example, imagine you want to bake a cake. You would need to buy the ingredients, mix them together in a certain way for specific amounts of time, put it all in the oven, and then let it cool. In computer programming, functions encapsulate all the steps of a process into one command. In this case, we might just have a bake cake function and throw all of these directions into this one function. Now, anytime we want to bake a cake, we just use this function without worrying about all of the specifics. Functions are also used to help organize and optimize code. Let's get started. Let's revisit the cylinder volume function, but with one modification. This function includes a default argument. If radius is not specified, then the variable radius will default to 5 when used in the function body. Calling the function like this would be the same thing as calling it like this, because radius is set to 5 if not specified as another value. Default arguments allow functions to use default values when those arguments are omitted. This is helpful because it can make your code more concise in scenarios where there is a common value you can use for a variable, although you still want it to be customizable. In this example, the default radius is 5, but we can still change this. This time, when we call the function, we are overriding the default value of 5 and calculating the cylinder volume for a cylinder with a radius of 7 instead. Also notice here, we are passing values to our arguments by position. It's possible to pass values in two ways, by position and by name. Each of these functions is evaluated in the same way. This one is simply taking the arguments by position, while this function is accepting arguments by name. There are some nuances for when you can perform the passing of values in each of these ways. You'll see more applications of this in the following quiz sections. As our first function, we'll write a function that calculates the volume of a cylinder. The formula for this is the cylinder's height multiplied by the square of its radius multiplied by pi. Here's what that formula looks like when defined in a function called cylinder volume. After defining the cylinder volume function, we can use it like this. This value is the volume of a cylinder 10 inches tall with a radius of 3 inches. Let's see how this works behind the scenes. A function definition includes several important parts. First, let's look at the function header. Defining a function always starts with the def keyword to indicate that the code that follows is a function definition, and ends with a colon. Following def is the name of the function, in this case, cylinder volume. This needs to be one word with no gaps. That's why this has an underscore. The rules for function names are the same as those for variable names. If you need a reminder on this, see the text below this video. After the function name are parentheses that enclose the arguments that the function expects, separated by commas. These arguments are values that are passed in as inputs when the function is called, and are used in this body. If you write a function that doesn't take arguments, then just leave these parentheses empty. Here is an example of a function that takes no arguments. In this case, there is no input data we want to work with in the body of the function, so no arguments are necessary. Next, let's discuss the body of a function. The body of the function is indented after the header, and is where the function does its work. Within this body, we can refer to the argument variables and define new variables. The pi variable that we define here is a local variable, meaning it can only be used within the body of this function. Attempting to access this variable outside the function isn't possible. This is due to what is called variable scope, which determines which variables you have access to in Python. We'll discuss this in detail later in the lesson. Often, the body of a function will include this return keyword, which is used to give back an output value when the function is called. The value of the expression that follows return is the output of the function. In this example, we return the value evaluated from this formula for the volume of a cylinder. Rather than returning the value as it is calculated, an alternative technique would be to calculate the volume earlier in the function body and then store it in a variable named volume. In this case, we would return volume like this. Functions like this can be imagined as little machines that take inputs or arguments and process them into output, or return values. This is a good image, but it's incomplete. Some functions, like print, don't return anything at all. Print displays text on the output window, but as we see here, the value it returns is none. None is what a function will return by default if it doesn't explicitly return anything else. The difference between print and return is often confused. Print provides output to the console, while return provides a value that you can store and work with in code later. You will get some practice with this in the quizzes that follow. It's not necessary that every function has a return statement. Notice this function, printGreeting, doesn't have a return statement, but it's still a valid function. Scope refers to which parts of a program a variable can be referenced or used from. If a variable is created inside a function, it can only be used within that function. Consider these two functions, word count and nearest square. The first function uses answer to count words in a document. The second function uses answer to track values while searching for the nearest square. Both functions include this answer variable, but they are distinct variables that can only be referenced within their respective functions. Alternatively, we might have a variable defined outside of functions, like this, and we can access it anywhere outside or within these functions. Scope is essential to understanding how information is passed throughout programs in Python and really any programming language. One of the key advantages of functions is that they can help break a program down into smaller chunks. This makes code easier to write and also easier to read because the pieces of your code, the functions, are reusable. If a program needs to calculate volumes of multiple cylinders, it can call this cylinder volume function multiple times, which is much cleaner than writing out the formula over and over again. Functions make code easier to read because they give human-readable names to processes. While the cylinder volume formula isn't that complicated, it is still harder to recognize than a precisely named function. There is an additional technique that makes functions more readable: documentation strings, or docstrings. Docstrings are a type of comment used to explain the purpose of a function and how it should be used. Here is a function for population density with a docstring. Docstrings are surrounded by triple quotes. The first line of the docstring is a brief explanation of the function's purpose. If you feel that this is sufficient documentation, you can end the docstring here. Single-line docstrings are perfectly acceptable. If you think that the function is complicated enough to warrant a longer description, you can add a more thorough paragraph after the one-line summary. The next element of a docstring is an explanation of the function's arguments. Here, you list the arguments, state their purpose, and what types the arguments should be. Finally, it's common to provide some description of the output of the function. Every piece of the docstring is optional. However, docstrings are a part of good coding practice. They assist you and future users in understanding the code you produced. You can read a more thorough explanation of docstring conventions in the link below. In Python, you can use Lambda expressions to create anonymous functions. That is, functions that don't have a name. They are very helpful for creating quick functions that aren't really needed later in your code. Later, we'll learn about higher order functions, or functions that take in other functions as arguments, where lambda expressions become especially useful. Let's compare the structure of a function and a lambda expression. Here is a simple function that doubles a number. It takes in a number x and returns x multiplied by 2. Calling double 3 would return 6. Here is the equivalent in a lambda expression. The lambda keyword is used to indicate that this is a lambda expression. Following lambda are one or more arguments for the anonymous function, and then a colon. These are equivalent, similar to the way argument names in a function are arbitrary. Last is an expression that is evaluated and returned in this function. This is a lot like the expression you might see as a return statement in a function. With this structure, lambda expressions aren't ideal for complex functions, but can be very useful for short, simple functions. If you want to specify multiple arguments in a lambda function, you can include them before the colon, separated by commas. Here's a lambda function that multiplies two numbers together. In the following quizzes, you'll get some practice using lambda functions and see how useful they can be. Congratulations on completing this lesson on functions. You learned about functions, variable scope, documentation, lambda expressions, iterators, and generators. Next, you'll learn how to write scripts in local environments with many functions pieced together. That's a lot of stuff. It's okay if you haven't mastered everything yet. You've already accomplished a ton by getting this far. We'll practice more of these concepts in the next lesson. Welcome to this lesson on scripting. Here, you'll learn how to combine all of the concepts you've learned throughout this course to write and run your own scripts locally on your computer. You'll learn about good scripting practices, working with raw input from users, reading and writing files, handling errors, importing local scripts, and working with different libraries. Let's get started. In all of the previous lessons, we've been using these boxes to represent a code editor where we wrote our Python code, and output window where we viewed results. And in the classroom, you use these programming quizzes to write Python and run your code. But instead of running your code online in the classroom, you can run Python on your own computer by installing Python and useful tools for your programming environment. Since Python is a popular open source programming language, it's free to download, change, and use. And the fact that it's already popular means there are online instructions to help you get it installed for most common operating systems. Because it's popular and open source, there's a large global community working on developing Python. For you, as a Python user, that means there will be new versions coming out as Python is improved by the community. You might find yourself needing to update Python from time to time, especially if you're collaborating with other people as you write Python programs that are compatible with the version they're using. Now, it's time for you to install Python. Now that you've successfully installed Python, let's try to run a script in your terminal. First, download the file firstscript.py attached at the bottom of this page and move it to an appropriate directory. I put my file here by dragging it from the Downloads folder to this folder. This might be a good time to set up a new directory for your learning if you don't have one already. Next, open your terminal and use cd to navigate to the directory containing the downloaded file. I can double check that the file is located here by typing ls or dir on Windows. Now that you're in the directory with the file, you can run it by typing Python followed by the name of the file like this. Then press enter. You'll know you've run the script successfully if you see this message. Whenever you type Python followed by the file name for a Python script, that script is run and the output is shown immediately afterwards. Once the code's finished running and all the output has been shown, your command line prompt reappears. Note if you type and enter just Python without a script to run, it'll start an interactive interpreter for Python. You'll learn more about this later. For now, you can just type in exit with parentheses to get out, or alternatively, Control-D on Mac and Linux, or Control-Z and Enter on Windows. Now I'm back to the command line prompt. It's your turn. Download the file below and run the script in your terminal. There are many ways to set up a programming environment, and there isn't a right or wrong way to go about it. However, if you're just starting out programming in Python, you might like to see this setup to get some ideas. Over here is a text editor. This particular editor is called Atom, but there are many additional editors I recommend in the notes below. A text editor is really different from a word processor, so don't mix them up. Code needs to be written line by line with intentional line breaks and indentations that fundamentally change how the code is read and run. Good text editors have simple but vital features such as line numbers and syntax highlighting. You can see the different ways Atom highlights a text based on the types of words and objects it recognizes from the Python language. Syntax highlighting really helps make code more readable and organized. It can also prevent us from making some syntax errors. For example, if I forgot a quote at the end of this string, I'll know I missed it when the rest of the line is highlighted like a string. Atom knows to use syntax highlighting for Python because of this .py at the end of the file name. This tells Atom it's dealing with a Python file. Editors are highly customizable to suit your style. One setting that I use is soft tabs with a tab length of 4. Which means that when I press tab, it's converted into 4 spaces. You can also add cool add-ons, like this Python linter that uses pylint to point out helpful things in my code. For example, in this line, pylint gives me a warning because I'm not following PEP 8 guidelines by including a space before my closing bracket. I also have this cool add-on which lets me use my terminal in my editor. Atom isn't the only thing on my screen right now. I do use this terminal add-on from time to time, but generally, I like to have a separate window for my terminal where I can run my scripts. Generally, I can't write a whole lot of code in one go because something will go wrong and I'll need to find the issue and debug it. When there's an error, it will show up here when I run the script. I make small changes to the code in the text editor and then run the script again to see the output. If I see a problem, I'll try to fix it, or if things seem to be working, I'll move on. I've also got the Udacity classroom and results from a question I Googled in my browser. Normally, I'll need a browser open to look up documentation or search for the solution to a bug I encounter along the way. From now on, we recommend that you try out all your code in this way. Put code into a new file in your text editor, and don't forget the .py extension. Make sure you're in the correct directory in your terminal, and then run your script. Now that you have your local programming environment all set up, it's time to try out different inputs. Programs can get a lot more interesting when they can interact with external information. First, let's try getting raw input from the user. Here's what I mean. This program prompts the user to enter a name and takes in that input as a string to use in its code. This input function is what takes in the user's input as a string. It has an optional argument that you can use to specify a prompt shown to the user. Since the input function interprets input as a string, you'll need to wrap the result with int or a float if you want to use it as a number. If you don't do this and try to use the input as a number, you'll get an error. Here, I wrapped the input with int and added 20 to it. But what if the user inputs a non-integer number? You can just wrap it as a float to catch non-integer numbers as well. But what if you need an integer, like if you're multiplying a string by it to repeat it a certain number of times? This wouldn't work with a float even if it's an integer number. We can actually wrap this int with float and then convert it into an int like this. Okay, that works. Clearly, trying to imagine and handle every possible case with user input can quickly get complicated. We addressed some cases here, but there are also loads of other cases we didn't address that could lead to more errors. We'll learn a better way to handle these scenarios in the next section. Before we move on to practice, here's another way we can interpret user input. Eval is a built-in function that evaluates a string as a line of Python. You can even include variables in the string like this. Now let's write some fun scripts that interact with user input. As you saw in the last video, trying to handle every kind of scenario when dealing with unexpected input can be a bit much. There's actually a much simpler way of dealing with this in Python. Here, you'll learn how to handle errors with try and except blocks. First, let's learn more about what errors in Python are. We've seen error messages due to several reasons in this course, and we can separate them into two types: syntax errors and exceptions. Syntax errors occur when Python can't interpret our code, since we didn't follow the correct syntax for Python. These are errors you're likely to get when you make a typo or you're first starting to learn Python. Here, I get a syntax error because I missed the ending quotation mark at the end of the string. I can see this in the error message: syntax error, end of line when scanning string literal. The other kind of error, exceptions, occur when unexpected things happen during the execution of the code. Here, although our code is syntactically correct, we run into an exception because the string spelling out 10 isn't a valid argument for the int function. There are different types of built-in exceptions in Python, and you can see which exception is being thrown here in the error message. Value error is one type of exception. It occurs when a built-in operation or function is given an argument with the correct type, but an inappropriate value. Here's another example that throws an exception. Here, we try to reference a variable name that we didn't define yet, so we get a name error exception. Again, this code is syntactically correct, but when Python gets to this line of code, it can't find the value for this variable when it tries to run it, so it raises an exception and stops the code. Here, the code in the except block occurs when any kind of exception occurs while executing the try block. Really though, we just want to address the value error exception. If I try to exit the program with Ctrl+C, it doesn't stop the program because the except handles any error, including the keyboard interrupt error. We can actually specify which error we want to handle, like this. Now it catches the value error exception, but not other exceptions like keyboard interrupt. Notice in this case, when I press Ctrl+C, it ends the program. This is because a keyboard interrupt exception was raised, which isn't handled by this try statement. Also notice that although the program crashed, this code in the finally block was still executed. Attempted input is printed no matter what, as the program is exiting this try statement, even if that means exiting the program. If we want this handler to address more than one type of exception, we can include a tuple after the except, with the exceptions like this. Or, if we want to execute different blocks of code, depending on the exception, you can have multiple except blocks like this. Here I have two handlers, one for value error and one for keyboard interrupt. When I press Ctrl+C, it says no input taken and breaks from the while loop. In Python, there are ways to handle exceptions so they don't always crash our program when they occur. Let's look back at this example that takes in input from the user. We saw that when we ran this code, it got an error when the user inputs something that can't be converted to an int. We can actually handle this error using a try statement. In a try statement, the code inside the try block is first run, and if Python runs into any exceptions while it's running this block, it will jump to the code in the except block. Here, if I run this code and enter the word 10, it prints "that's not a valid number" and moves on to the rest of the code. The program continues to run whether or not it runs into an exception during this try block. For example, if I have a line after this try statement that prints attempted input, you'll see this is printed in both cases. If we want this code to keep running until the user inputs a valid number, we can use a while loop and break the loop if all the code in the try block successfully executes. Here, the program keeps taking in input until I enter a valid number. If I enter a valid number, this statement in the try block doesn't raise an exception, so it moves on to the next line, where it breaks from the loop. However, since it breaks from the loop, it never prints attempted input. If we want this last line to always run after the try statement no matter what, there is an optional component of the try statement we can use. Finally, now attempted input will be printed when the program is exiting this try statement under any conditions, whether there's a break statement, return statement, or error that causes this program to crash within the except block. You can read more about this in the notes below. The finally block is useful for cleaning up actions in your code. Later in the lesson, we will use this to close a file after attempting to open one in a try statement. Let's see how we read information from a file into Python. To read from a file, we first need to open it, which we can accomplish with the built-in function open. We include a string with the path to the file, along with any optional parameters we want to specify. The open function returns a file object, which is a Python object through which Python interacts with the file itself. Here, we assign this file object to the variable f. This second optional parameter specifies the mode in which we open the file. In this case, R, or read only. We are using this mode since we only want to read from the file. We don't want to change any of its contents. This parameter isn't really necessary for us to include here though, since the mode defaults to read only if unspecified. Once we opened our file and created a file object, we can use the read method to access the contents of this file. This read method takes the text contained in a file and puts it into a string. Here, we assign the string returned from this method into the variable file data. When we are finished with the file f, we should close it. This will free up any system resources taken up by the file. Here's an example that uses this file, sumfile.txt. It's important to remember to always close files we have opened once we no longer need them. If we open a lot of files without closing them, we can run out of file handles, and we won't be able to open any new files. Exactly how many files you can open before running out of handles will depend on your operating system. To convince yourself, you can try running the following script in Python. At some point for a large enough number, you will receive an error. We can see that at 7,164 open files, the system no longer had available resources to open any new files. To avoid this, it is always a good idea to close any files you no longer need. Opening a file object is like opening a window to look into a file. To be more precise, it's a window that's only one character wide, and it always starts off at the very start of the file. This is very different from reading a book or a document where you can look at multiple words or even pages at once. Think instead of the file as a long stream of characters. The file object can look at just one character at a time in order. In addition to reading from a file, you can also write to a file, in which case you will change the content of the file. To do so, you must open the file in writing mode. Be careful once you open a file in writing mode. Anything that it contained previously will be deleted. If you're interested in adding to an existing file without deleting its content, you should use append instead of write. You can visit the Python documentation for more information on the different modes in which you can open a file. Since we're in write mode and I don't want to delete what's in this file, let's use another one. If the file does not exist, Python will create it for you. We can now write to the file like this. And after we're done, we will close it like good citizens. Here, you can see that Python created another file which contains the text hello world. It could be easy to forget to close a file when you're done using it, so Python provides a special syntax that auto-closes it. This with keyword allows you to open a file, do operations on it, and automatically close it after the indented code is executed, in this case, reading from the file. Now, we don't have to call f.close. This code, as f, assigns the file object created by the open function to the variable name f. This line of code is basically this line of code, except you can only access the file object f within this block. This is another kind of scope. Once you leave this indented block, the file is closed and you are no longer able to interact with it. For example, trying to call f.read outside this block like this would return an error. However, just because you close the file doesn't mean you lose the data. Here, we read in the file in this line and get this file data string that has the text contained in the file. Calling file data outside the block works fine. We can use all the usual string methods on this file data string to process its contents. In order for a program to be really useful, it needs to interact with real-world data. Images, web pages, and databases are all examples of files, and we routinely create, move, manipulate, and read these files in our daily digital lives. All the data we've used so far has been defined inside the Python script or raw input from the user during execution of the script. Next, we're going to massively increase the variety of what we can achieve in our Python programming by introducing how to read and write files in Python. This will allow us to interact with and process larger amounts of information from many more sources. All kinds of files have a similar structure on a computer. They are strings of characters that encode some information. The specific file format, often indicated by the extension of the file name, such as .py, txt, htm, csv, and many more, will indicate how those characters are organized. The characters in a file are interpreted by the various programs we use to interact with them. For example, an image editing program will interpret the information of a digital photograph file and display the image. If we then edit the image in the program, we're using this program to make changes to the characters in the file. In Python, we can read those file characters directly. The experience will seem quite different from opening a file in a desktop application. Opening files in Python gives us a common programmatic interface to all kinds of files without the need for a graphical user interface, which means we can automate tasks involving files with Python programs. Awesome job completing this course. After covering lessons on Python's data types and operators, control flow, functions, and scripting, you've developed the understanding and skills necessary to tackle projects and courses in Python. Congratulations again on completing this course. If you recall from the previous lesson, iterables are objects that can return one of its elements at a time. Lists are one of the most common iterables you have used. It turns out many of the built-in functions we've used so far, such as enumerate, return something called an iterator. An iterator is an object that represents a stream of data. This is different from a list, which is also an iterable, but not an iterator, since it is not a stream of data. Soon, you'll see some reasons that iterators are favored in different situations. Here, we will learn how to create iterators using generators. Generators are a simple way to create iterators using functions. However, it's not the only way to create iterators. You can read more about this in the notes below. These terms may be a little confusing. The term generator is often used to refer to the generator function, but it's also used to refer to the iterator object produced by the function. Here, I'll differentiate these by referring to the function as a generator function and what it produces as the iterator. Here is a generator function called myRange that produces a stream of numbers from 0 to x minus 1. Notice that instead of using the return keyword, this uses yield. This allows the function to return values one at a time and start where it left off each time it's called. This yield keyword is what differentiates a generator from a typical function. As you can see here, calling myRange4 returns an iterator that we can then iterate through. Using a for loop, we can print values from this stream of data. Here, this prints 0, 1, 2, and 3. In the next section, you'll get some practice writing generator functions to create your own iterators.